ideal gas law. This is a formula for the ideal gas law, and this formula works best, as you hopefully would guess, with ideal gases. Now remember, ideal gases follow the assumptions of kinetic molecular theory. But also remember, real gases don't always behave ideally. This is going to work best for ideal gases, but they don't always behave ideally. So that's just something to keep in the back of your mind, okay? Why don't they always behave ideally? Because real gases have volume. They don't have negligible volume, they have volume. And real gases do attract or repel each other, okay? But again, we're dealing with ideal gases. We're looking at how gases are going to behave. Okay, so this is our formula we're going to be using to calculate either pressure, volume, number of moles, or temperature. Notice I only have 4 variables here, but you see 5 letters. That's because R is a gas constant. Now, scientists over the years have done hundreds of experiments to determine that if they know the values of PV, N, and T, if they know pressure, volume, moles, and temperature, they've been able to figure out what the R value is. Okay, now R is a gas constant. We're never going to be solving for a gas constant because we know the values of R depending on what pressure we're dealing with. So what that means is if we're dealing with a pressure that is in kilopascals, kPa, then our R value that we're going to plug in, which has been scientifically determined experimentally, that R value is always going to be 8.31, and the unit is liters times kPa over moles times K, Kelvin. Long unit, okay? If this P value that we're dealing with is atmospheres, then the R value we're going to plug in is 0.0821 liters times atmospheres over moles times K. If this P value is millimeters of mercury, our R value is 62.4 liters times millimeters of mercury over mole times K. You get the idea. Notice that the only difference, besides the values for R, but the only difference in their unit is the pressure unit, okay? That's the only difference here. Now, the reason that we have different values and different units here is because if my pressure is in kPa, I need that kPa to cancel out. So my unit here has to have kPa. If the pressure is in atmospheres, I need atmospheres to cancel out in order to solve for one of these variables. So my unit here needs to have, does us no good if this P is in atmospheres and this P is in kPa, because we can't cross out kPa and atmospheres. They're not the same unit. It's like trying to cross out or cancel out grams and milligrams, okay? Not the same unit, so you can't cancel them out, okay? So these are the R values that we're going to be seeing and working with. Let's see a couple of examples. The second problem I have here is working with the ideal gas law. Remember, PV equals nRT. You'll get so used to saying that you'll be sick of it. PV equals nRT. Here's my problem. A steel container with a volume of 2 liters is filled with nitrogen gas to a pressure of 2.00 times 10 to the 4th kPa at 28 degrees C. How many moles of gas does a cylinder contain? Okay, let's do a little bit of labeling here. I have a volume of 2 liters, okay? It doesn't say that any of my values are changing, so I'm not going to label these as 1 or 2. This is my volume, 2.0 liters. It's filled to a pressure of 2 times 10 to the 4th kPa, so I have pressure. At 28 degrees C, I have temperature. How many moles, this is what we're looking for, N, does a cylinder contain? All right, now just because I think it's a good practice, I'm going to put my variables list here. So P is equal to 2.00 times 10 to the 4th kPa. V is equal to 2 liters. N is what we're finding. R, we need to find our gas constant. Our pressure is in kPa. So we want to find the gas constant that uses kPa, which is right here, 8.31. Okay, so our R value here, our gas constant, is 8.31, right? And look at our unit, liters times kPa over mole times K. Liter times kPa over mole times K. The last thing I need to label here is T. T is 28 degrees C. Now, remember, in gas laws, you need to be converting to Kelvin. So I need to add 273.1 to get, I think I've worked this out, 301 Kelvin. That's my temperature. Now I have 3 of my 4 variables and I have my gas law constant, so I can work this out. Now, here's what we're looking for, N. I'm going to say the easiest way to do this is isolate N before you plug anything in. How you do that is divide both sides by RT. RT cancels out over here. And you get N is equal to PV over RT. That's the formula I'm going to use now. Okay? So over here, I'm going to go N is equal to P, 2.00 times 10 to the 4th kPa, times V, 2 liters, divided by R, 8.31. Do you need to write the whole unit? Sure you do. We need to see that the units are canceling out. So write this whole unit. Liter times kPa over mole times K times T. And my temperature that I already figured out is 301 K. Okay, let's see if the units cross out. kPa, gone. Liters, gone. Kelvin, gone. The only unit I'm left with here is moles. Right? Now when you do that math, you get 160 moles of nitrogen gas. And of course, we want to make sure that we are including a decimal here because we want to show 3 sig figs. We have 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. So our answer, 160, needs to have that decimal place. That's it for ideal gases. I hope that wasn't too much. We'll have a lot of time in class to practice this. Thanks guys for watching.